Welcome to today's WESTPAK webinar, Sustainability Part 2, How to Engineer a Cushion Using Molded Fiber and Replace Your Foam Cushions. My name is Roy Strinnen. I will be the moderator for today's webinar. A few housekeeping items before we start. All attendees are muted and will remain muted for the duration of the webinar. Next, let's take a moment to ensure that everyone is ready and familiar with the webinar control panel. You should have a control panel on the right side of your screen. You can minimize this panel by clicking on the orange arrow button in the upper left corner. You can expand the panel by clicking on the same button. You can submit questions at any point using the chat pane located near the bottom of the control panel. We'll be answering questions after the presentation. If we are unable to address all the questions, we will follow up by email afterwards. For those registered and logged into the webinar, you can download a copy of the slide deck now. Look for it on your webinar control panel. Okay, let's get started. We are very fortunate to have a very qualified presenter today. Greg Schwinghammer is a principal engineer at WESTPAK, a 100% certified employee-owned company. With over 20 years of experience at WESTPAK, Greg held roles ranging from test engineer to general manager. His primary focus is ensuring customers receive the highest quality service and timely results for all testing projects. Recognized as a go-to expert in the field, Greg provides trusted guidance on test protocols, equipment capabilities, and package design optimization. He is an active member of ASTM Committees D10 for packaging, F2 primary barrier packaging, and E60 sustainability. He holds a packaging dynamics professional certification from ISTA. I'm going to give the microphone over to Greg to begin the presentation now.
Great, thank you, Roy. Kind of the agenda for today, we'll kind of give an overview of WESTPAK and then kind of what is the purpose of packaging, review of damage boundary and cushion curves, development of cushion curves for molded fiber, and kind of looking at it from a standpoint of other novel cushioning materials that may be more sustainable than the standard polyethylene or EPS foam cushions. And then comparing molded fiber to a foam cushion and reviewing a study that was conducted back in 1994. So WESTPAK, as Roy said, is a 100% employee-owned company. We were founded in 1986 and we'll be celebrating our 40th anniversary later this year. I hope you can all join us for that. We run about 3,000 projects through our 3 locations, 2 in the Bay Area, 1 in San Jose and 1 in Union City. And we have our 3rd location in San Diego. Though we're located just in California, we serve customers across the country and around the world. We're an ISTA certified lab and we're ISO 17025 accredited through A2LA. So now for a bit of review, if you want to see a deeper dive on using damage boundary testing, you can view our previous webinar at westpak.com under the resources tab. So why do you need a package? So the environment puts a certain amount of energy into your product, whether it's drop, vibration, temperature, humidity, altitude, solar radiation, anything may be affected by the distribution environment. What we see here is a qualitative representation of how severe the distribution environment is. This is different, like I was saying, for all different types of shipment. But at the end of the day, imagine this bar represents all the inputs that your product will see in the distribution environment. The bare product can take a certain amount of that distribution environment. So it has a certain ruggedness to drops and vibration and all the other inputs I mentioned. And the purpose of the package is to make sure that your product can absorb all those inputs. It adds extra protection around the product's capabilities. What happens if you don't have enough packaging to protect your product? Your product will be damaged in that distribution environment. And another thing that can happen is you can have too much packaging, which then results in waste and over expense. One other thing you can do to help reduce the amount of packaging you need is you can increase the ruggedness of the bare product and reduce the amount of packaging you use overall. So looking at this is more rugged products. So you may need to spend a little bit more on the product design and development of the bare product, but you can make it more rugged. So what is damage boundary? Damage boundary is a method of determining the ruggedness of your product, or in other words, the fragility of your product from shock. What damage boundary is usually used for typically, it's done on equipment that needs an engineered cushion system, but anything can benefit from this analysis. We've done damage boundary testing on medical devices. We've done damage boundary testing on combined product, medical device and drug product all in one. We've done damage boundary testing on computer products and household items. So really, you can use damage boundary to figure out the fragility of your product. Why would you want to use damage boundary testing? When you know the ruggedness of your product, you can determine how much packaging is needed, or if packaging is needed at all. If your product is rugged enough to survive that environment, from a shock standpoint, you may not need a package to protect it against shock. You also can determine how much you can reduce your packaging and still protect your product if it's a system you're already shipping and you're stuck with trying to reduce the amount of packaging you need. This will help you make data-driven decisions for that. So what does a damage boundary curve look like? When you have conducted the damage boundary test, this is what the damage boundary curve looks like. Like I said previously, if you want a deeper dive on this topic, check out our previous webinar. The horizontal axis is the critical velocity change, and the vertical axis is the critical acceleration. So velocity change is in inches per second, and acceleration is in Gs. The area highlighted as the damage region is the area you need to protect your product from, and the area you design your cushion system to be outside of, now that you can make data-driven decisions about your package design. For our product here, let's say the critical velocity change is 70 inches per second, and your critical acceleration is approximately 80 Gs. Remember this, we'll be using it later for examples. So 80 Gs, 70 inches per second is where our product fails at. So we need to be below those numbers to be outside that damage region. So now let's talk about cushion curves for molded pulp. And like Roy said, if you have questions as we go, please stop and send them in the chat, and we'll have time at the end to hopefully answer a few of the questions. As long as I don't ramble too long. I tend to ramble sometimes. So what is a cushion curve? A cushion curve is a method for obtaining dynamic shock cushion characteristics of packaging materials from accelerated time data. That's a bit complicated answer. So more practically, it gives you guidance to packaging engineers on what to expect from a given cushion from a given drop height. If the product engineers have done their damage boundary test, like we talked about previously, they will have what the critical acceleration is for the product and be able to use that information in conjunction with the cushion curves, which allow them to choose the optimal material and thickness to best protect the product using the least amount of material. This cushion curve is for an 18-inch drop for I think it's a 2-pound polyethylene foam for 2-inch thick, 3-inch thick, and 4-inch thick. So let's look at how to read a cushion curve. The x-axis is the static loading in pounds per square inch, or PSI. The y-axis is in units of Gs, or deceleration. And this curve here is for 1.2 pound per cubic foot. That's the density of the material, polyethylene foam cushion for a drop height of 30 inches for thicknesses of 1, 2, and 4 inches. As you can see, cushion curves are very specific for a set of scenarios. It's a thickness of material, a density of material, and a given drop height. How to use this curve? First, you find the curve that best fits your deceleration level for what you're looking for to be below. So ours was 80 Gs. So the 1-inch thick material here wouldn't meet our needs. So I think either the 2 or the 4-inch thick material, we could load this to be below 80 Gs. And you want to do what's called load the curve between these two lines in the belly of the curve. So anywhere from 0.4 psi to 1.4 psi. And remember, we're looking below 80 Gs. So to use the least amount of material, we'd use the 2-inch thick material loaded between those two lines. So second, you will need to determine how much cushion you will need. Wow, that's a lot of you will needs. So you take the weight of your product. Let's say your product weighs 20 pounds, and you would divide that by the static loading. So if we loaded it at the 0.9 level, so if you look here, it's a 0.9, gets us down below 60 Gs for the 2-inch thick material. That would be 22 square inches of foam. And we can get into later how that works. If you have questions on that, we can talk about that. So now let's look at developing cushion curves and how you would do that for molded fiber and for other novel, more sustainable cushion systems. There are 3 main standards for developing cushion curves: ASTM D1596, ASTM D4168, and ASTM D3575. And each of them has a different technique and methodology for developing the cushion curves. So today we're going to look at modifying D4168 and using it to develop cushion curves for molded fiber. So hang on, move this. So make sure I hit all the topics I want to talk about. So looking at molded pulp, as a solid material, pulp cushions generally have poor dynamic properties because of their relatively high stiffness and lack of compressibility. Pulp becomes a legitimate cushioning material primarily as a function of its shape and deformation or crushing of that shape, assuming that the material can be characterized as a rectangular prism and functions as in a compressive manner. So if you have a large block of molded fiber, that's not going to work as a cushion. You need shapes and something to deflect to be able to give that cushioning property like a polyethylene or EPS foam. Since pulp cushions are dynamic, pulp cushion dynamics are largely shape dependent. New or modified procedures are required in order to determine its impact and vibration performance properties. The procedure established for testing described here is a modification, like I said, of ASTM D4168, the procedure commonly referred to as the enclosed block test method. Its original design and purpose is of testing of foam in place materials or foam in place cushions, but we've modified it here to be able to use it for other materials. If we find that there's enough traction for this, we can work with ASTM and modify the standard to include doing testing on non-standard or more sustainable cushioning materials. This procedure requires the use of a block. So you can see the block here that you can add weight to. And then you have an accelerometer on the top of the block. And then underneath are your foam cushions. So you have a certain weight over linear inch of material. So you would measure the linear inches of the cushioning material or the molded fiber underneath, and you would have that. So how do we determine the equivalent drop height using this system? The equivalent drop height can be calculated using the formula height, H is equal to V squared divided by 2G, where H is the height, the drop height, V is the velocity change, and G's is the gravitational constant in units of inches per second squared. The response deceleration transmitted through the cushioning material and to the test block will be monitored using the response accelerometer mounted on the top. So what does that look like? To conduct the cushion curve from molded pulp material and others more sustainable cushions, you should take this system, place it on the platen of the shock machine here, and then drop it from a given drop height based on the velocity change. Following the general accepted cushion test procedure, 5 impacts should be conducted at each loading level. So each time you add weight to it, You do 5 impacts. The first impact is recorded, and you take the average of 2 through 5 for developing the cushion curves. The loading levels should be recorded for each weight per linear inch rather than pounds per square inch, like I mentioned before, which is the normally accepted procedure. This test should be conducted on cushions with normal moisture content of 7% and high moisture content of approximately 13%. Therefore, proper conditioning of the samples is essential. Similar, the testing should be conducted on any expected combination of recycled content, as the amount of recycled content may affect the cushioning properties of molded pulp materials. That said, if there's enough of these developed and a supplier can find that recycled content doesn't affect it, you then can reduce the amount of cushion curves you're doing. So this table shows an example of cushion curves for a 36-inch drop height. The 3 curves represent 3 different thicknesses of molded pulp material. The x-axis, like I've said before, is static stress, and the y-axis is deceleration in Gs. The graphs were derived using the test method we talked about on the previous slide. As mentioned previously, when using this type of graph as a design tool, you should first know the fragility of your product. Once you determine the product's fragility, you can use the cushion curves to find the optimal loaded cushion system for a given drop height. Now let's look back at what we were using before for our product from slide 9, which had a critical acceleration. Anybody remember? Put it in the chat if you remember. That's right, 80 Gs. Any of these materials, when properly loaded, would protect the product from impacts from impacts for a 36-inch drop. Because you can see 80 Gs is all the way up here. So we could use thickness 1 and still be in the 60 G range. So kind of going back in history, 1994 study of cushioning properties of molded pulp was conducted by Dan Eagleton and George Marcondes. It was published in Packaging Technologies and Sciences, Volume 7, 1994. It compares the cushioning properties of expanded polystyrene, or EPS, to molded pulp for shock performance characteristics. The study found that a static loading between 0.29 2 kPa and 0.58 psi, or 4 kPa, for molded fiber cushions performed as well, if not better, than the EPS cushioning material loaded at equivalent pounds per inch. At loadings above 0.58 psi, the EPS outperformed the molded pulp. The study concluded that molded pulp is best used for low drop heights and low static loadings. If we use our product from slide 9, which had a critical acceleration, it was one slide ago. Does anybody remember what that critical acceleration was? That's right, again, 80 Gs. Any of these materials, when properly loaded, would protect the product from impacts of 36 inches. So you can see here on this graph, it's the 2 molded pulp cushions that are pictured here on the right. And in the belly of the curve, they're both below that 80 G deceleration level. And the EPS, if you had to load it out higher, is already below that as well. So looking at this, I think there's plenty of room. And if there's people on here from universities or molded fiber companies, I think there's room for a lot of research that can be done in this area and better engineering of molded cushions from the 90s. There's probably AI that can be used to engineer these cushion systems, and we can help build these cushion curves for a more sustainable package system. And if you have other materials that could be used for more sustainable packaging, you can use the same methodology to develop those cushions. So kind of in summary, remember you can use damage boundary and cushion curve data to engineer the optimal package for your product. You can develop cushion curves for non-standard cushioning materials like molded fiber materials by modifying the procedure called out in ASTM D4168. And in the Eagleton Marcondes paper, they found that molded fiber cushions were as good, if not better, than EPS when loaded between 0.29 and 0.58 psi, and for decelerations levels above 80 Gs. for a drop height of 12 inches. For higher drop heights and lower deceleration levels, more research is needed. Like I was saying, engineering of molded fiber and other novel materials, more sustainable materials, would be good to drive sustainability. That's all I had. Roy, did I do perfect, or do we have questions?
You did excellent. And we do have time for a few quick questions. So
Cool.
Here's one. Do you know of any other research that has been conducted since that paper was published in 1994?
I had done a research, or I did research to find if there had been any other research conducted. I wasn't able to find any other cushion curve research that had been done for more sustainable cushioning materials for cushion curves. It may be out there, and it may be locked away with certain companies, and they haven't published the data. But just on the open market, I couldn't find anything since 1994.
Okay. A second question. That's great information to use when engineering a cushion system for drop testing. Is there any way to do the same for vibration testing?
That is a good question. Yes, there is a way to do it for vibration testing. You would take that same test block and put it onto a vibration table and do the same loadings as you would with a cushion curve. And so you would put the block on and you would do a sine sweep from, let's say, 1 to 200 hertz that would be similar to what's in the distribution environment, to see where that cushioning material resonates at. And then you could plot that as a transmissibility plot for those same materials. So you could do it for vibration and for shock. But we just talked about shock here today. If that person has any more interest in that, reach out to me and we can talk about doing that type of testing for them.
Great. Let's squeeze in one more question. It says, the G level seems so high for the cushion curves of molded pulp. Why would I use this material instead of foam cushions?
You would use this material instead of foam cushions because it's a more sustainable, it's 100% recyclable material. And if you know the fragility of your product and it fits into the cushion curves that are developed for molded fiber, then that would meet that requirement. Thinking through it a little bit more too is, if you go to a molded fiber supplier and ask them for cushion curves, they should hopefully be able to engineer a cushion curve or a material that meets the deceleration requirements of your product.
Okay. Well, thank you, Greg, and thank you to all who attended and submitted questions. We truly appreciate each one of you. For anyone whose questions did not get answered, we will respond to you directly by email within a few days. If you missed anything or would like to listen to the webinar again, please go to our website, westpak.com, under the resource section and the webinar tab. The webinar materials will be uploaded within the next couple of days. Thank you for attending today's